Good evening, everyone. Welcome back. We're so happy to have all of you here tonight and starting on a new ASHRAE term. So to start off as usual with a few announcements. All right, so we want to say thank you to our sponsors, Carrier, Con Edison, WSP, CDE, SRS, our partners, Train, Fulcrum Group, Goldman Copeland, Tech Systems, JB&B, Mitsubishi, IKEA, Siska Hennessy, ADE, Fleet, Technical Air Systems, Belimo, our supporters, ADS, Chimney Design Solutions, Federal Pump, Schneider Electric, Johnson Controls, National Air Filter, Victaulic, Cerami, Wallace Ennis, Siemens, Dakin, Thermal Systems Associates, Skyline, EcoCare Corp. As you guys may know, this year ASHRAE is celebrating its 125th year celebration. And the first meeting was held in New York in 1894. And we're going to have now a welcome message from this year's chapter president, Tony.
Thank you, Natalie. Good evening, fellow ASHRAE members. Welcome to another Society Year. My name is Tony Sang with Federal Pump, and I have the pleasure of being the chapter's president this year. My presidential theme is continuity, collaboration, and consistency. Since March, our lives have been filled with uncertainty for the future. For some, the career path might look vastly different today, and for others, you have to adapt to learning without tangible campus. But for everyone who's joining us tonight, there is one thing that we all share and is certain, and that is the desire to learn. So welcome. I believe that it is ASHRAE New York's obligation to create this continuity of education, the sense of normalcy, and the sense of normalcy for our membership. Natalie and Michael, who are our program chairs this year, have done a wonderful job to date, and we wouldn't have tonight's webinar without them. So thank you. And while we're physically alone more than ever, we've also found collaboration is more important than ever. Our Young Engineer and ASHRAE committee has never seen the growth in participation at today's rate. And we're only starting the year. Luke and Kim have done a great job with our social media and sharing activity with our younger members. There are many of us who want to volunteer our time for the betterment of society. So we will be posting our committee meeting times on our website's calendar for those who want to join us to give back. To sustain our strive for normalcy and teamwork, we must create consistency. So keep expecting the emails for Cross-Learning Alliance programming. Keep expecting the exciting topic for every fourth Tuesday of the month, and keep expecting our newsletter for the committee's chair's next endeavor. While I cannot promise when we'll have our in-person dinner meeting, like we did last year, as you see it in our slide, I can promise the continuity and collaboration that you could count on consistently. Thank you.
Thank you, Tony. Few other announcements. We have a Cross-Learning Alliance event coming up starting on October 12th. This is with association with AIA. It's a multi-day event, it's October 12th through the 16th, and it will be on Local Law 97. If you are interested in signing up for this event, please see our website. And also next month, I'm excited to announce that we will have the ASHRAE president, Chuck Gulich, visiting us. So please look forward to additional information. We'll probably have a virtual happy hour / meet and greet so everybody can get a chance to talk to the society president. He will be our guest speaker for the dinner meeting. All right. Few items before I introduce our speaker and start tonight's presentation. Please do not forget, if you need PDH credits, complete the poll at the questionnaire at the end when you close out of the webinar. This will keep track. If it does not pop up at the end, please just email us, and I will make sure with your name, address, and a few other with the other information that we would need typically, and I will make sure you are on the list and you get the certificate. Also, for our question and answer period, please use the questions box on your control panel, and I will be monitoring that throughout the presentation. Sorry. Tonight's speaker is Noah Rauschkolb. He is a Ph.D. candidate at Columbia University. His dissertation focuses on the design of electric tariffs, on how electric tariffs can be used to promote efficient adoption and operation of distributed energy resources. Before starting his PhD, he was an engineer at ARUP. So please welcome Noah, and I'm going to give him control.
Oh, hello. Can you hear me? I think so. So thank you so much for having me. As Natalie said, my name is Noah Rauschkolb. I'm a fifth-year PhD student at Columbia. I have been a member of ASHRAE since 2014. And in 2015, I was sponsored by ASHRAE to research policy for energy efficiency in multifamily housing as part of the Washington internship for students of engineering. Which for me really set me on this path that I'm on now of looking at engineering, policy, economics, all as part of an interconnected system. So that ultimately was a really big factor in leading me to my PhD topic, where I am looking at distributed energy resources and really how we can move to a lower carbon economy. I'm a member of the Sustainable Engineering Lab here at Columbia. And today I'll be talking really about two different interconnected projects, both of which dealing with the economic and technical viability of wider adoption of heat pumps in residential homes. And I'll say right now, if you have questions, you can just put them in the chat throughout and I'll try to respond to them. If you've got a question on your mind, I'm sure many other people do. So I'll just try to catch those as we go. Session objectives, really the first half of the talk, I'll be talking about some research that I presented at ASHRAE Orlando back in February. So if you missed it, this is basically a recap of that. From that first part of the talk, you should be able to identify the potential emissions benefits of heat pump systems, specifically thinking about dual fuel heat pump systems, and then estimate the electricity price required to recover a dual fuel heat pump investment. In the second half, I'll be talking more about the electric utility. How do we have the prices that we have today, and the different kinds of volumetric charges or demand charges or what have you, why it has worked as well as it has in the past, and why might it not work very well in the future when we're thinking about a more dynamic grid with more dynamic buildings. So from that second half, hopefully you'll be able to take away some of the basic economics of utility rate making and then understand the expected load impacts of heating electrification in particular. Great. So there's been a lot of talk about smart buildings, more smarts, smart grids, smart everything. What's available right now? So if you go onto Amazon for 118 bucks, you can get 2 light bulbs with a dimmer switch and this little Phillips box here, which connects it to your Wi-Fi. I've spent a lot of time playing around with these early on in my PhD. They're very cool, but they're light bulbs. What else can you buy? You can buy an Alexa-enabled microwave. You can get lots of smart outlets. They even sell on Amazon a smart bidet. I don't want to know much more about it than that. The issue is if you add up all of the energy use from these things, it's really not that much. So this is data from the Energy Information Administration, which does a survey every 4 years called the Residential Energy Consumption Survey. This is 2015 data. We are waiting patiently for the 2019 data to come out. And if you add up all of your lighting, refrigeration, and all your other plug loads, it's less than 30% of the average energy consumption in a US home. The lion's share of residential energy use, and I know commercial energy use is balanced a little bit differently, but for residential, upwards of 60% of energy use is for space and for water heating. So the trouble there is that we can do all of this work to clean the grid. We can build lots of wind and lots of solar and figure out batteries and do all kinds of cool seasonal stuff. And we can do all that. And maybe we can get to a grid that's very close to 100% renewables, but we will have done nothing to reduce the emissions coming from space and water heating that is produced through direct combustion of fossil fuels, which is most residential space and water heating comes from direct combustion of mostly natural gas and a little bit in the oil, mostly in the Northeast. So there are multiple approaches to dealing with this. The one that I have been focusing on the most is electrifying the heating in buildings and then providing that with clean power. So we're all HVAC engineers. I'm not going to spend a ton of time on technology. Broadly, there are 3 technologies: electric resistance, cheap but inefficient; ground source heat pumps, very efficient but very expensive, especially for retrofit jobs; and then air source heat pumps are what are most exciting to me because they're essentially just a 1-for-1 replacement with existing split systems, whether a mini split like this or a full DX split system that you'd see in a forced air system in a home. Why would electrification decrease emissions? So if we just start with 10 therms of natural gas and we put it through a traditional furnace, we'll get out 117 pounds of CO2 and 800 kBTUs of heat. That's kind of the starting point. Now, if we have a condensing furnace that's 96% efficient, the emissions are the same, but you get 960 kBTUs of heat. That's a 20% improvement. And that's basically, you know, if there's been a big improvement in the last 20 years, it's this. It's that we're using more condensing furnaces. On the other hand, if we took that same gas, we put it through a combined cycle gas turbine, which is about 60% efficient, we get out our same CO2 emissions, but we get 176 kilowatt hours of electricity. Now, what we do with it matters. If we put it just through an old school electric resistant spaceport heater, we'll get out 600 kBTUs of heat, and that's really our worst case. That's worse than just burning the gas on site. On the other hand, if we put it through a heat pump with a COP of 3, we can get out 1800 kBTUs of heat, which is worlds better than any other option on the page. So at least as far as the back of the envelope is concerned, there seems to be some potential for heat pumps. Now, having said that, the actual estimates for heat pumps are pretty modest. This is data from the US Energy Information Administration's annual energy outlook, where they project out the next 30 years or so. And you see that for residential space heating, the energy use, and this y-axis is in quads, these lines don't cross. You know, we see modest decreases in demand across the board. Most of that is just a product of energy efficiency, but they don't see any big uptick in space heating. So let's say you're burning, you know, 3 3/4 quads today, and you'll be burning 3 1/4 quad in 30 years from now. You're still bound to chemistry. So you're not going to dramatically reduce the emissions from that. It's still a direct relationship between how much you burn and how much CO2 you get. Water heating, the projections are basically the same. We're not seeing the same energy efficiency benefits because water heating is already pretty efficient. So we're actually seeing a modest increase in natural gas consumption there, which would lead to a proportional increase in emissions. So coming from the starting point that heat pumps seem really promising, and yet the current estimates don't project that they're going to be widely adopted, I started asking, well, why? You know, first of all, is there something I'm missing? maybe I'm overestimating the actual emissions benefits. So the first question is, what are these emissions benefits of heat pump adoption when we look at different climates? And then the second question is, what are the economics? We're specifically thinking about hybrid, also called dual fuel or bivalent heating systems. And basically the strategy with a hybrid system is, if you've got an existing home, and most of the buildings we have in 2050 are the buildings we already have now, after say 15 years, your AC split system breaks, you replace it with a heat pump. A heat pump could be exactly the same size. If you've got a 2-ton AC, it could be a 2-ton heat pump, could be bigger if you want to heat it to a slightly lower temperature. You retain your furnace as a backup for those really, really cold days. The advantage there, and I think you guys mostly know this, is heat pump COPs, the efficiency, really degrades when ambient temperature drops. So you would need a much bigger heat pump to heat a building down to say 20 Fahrenheit than you would to heat it to 30. And the further you go in those extreme situations, you need bigger and bigger heat pumps, and they're operating less and less efficiently. The big thing, I think the big sell for this project, and the reason it was pretty well received at ASHRAE Orlando, is because we looked at every climate region in the United States. So according to the International Energy Consumption Council, International Energy Conservation Code, they give us 16 different climate regions, varying both in your average temperature and in moisture. So I'll just go straight forward to the results and what we found doing these simulations. And basically we did these simulations in Energy Plus, taking the same building model, moving it throughout the country, and basically just changing the weather and changing the heat pump capacity, and then doing the math on what it would actually cost to run these things. So each of these different tiles is a different example city, representing a different IECC region. So 1A, Miami, very little heating demand. 3C, San Francisco, more, all the way to Duluth and to Fairbanks. The two different colored bars. So all of the orange bars represent natural gas homes, homes that are currently heated by natural gas. The red bars are homes that are currently heated by fuel oil. And for each of these tiles, the first set of bars shows the base case, where we just replace your old AC that's dead or dying with a new AC system and continue to get all of your heating energy from whatever the incumbent fuel is, natural gas or fuel oil. And then the second bar is, well, what if we say for this home in Houston, where the minimum size for the AC was a 4-ton unit, what if we replace that 4-ton AC with a 4-ton heat pump? What would the emissions impacts be? Now, despite the huge variance in climate regions we looked at, we actually found pretty consistent results here. And that was really across the board. There are huge emissions benefits to just that first change from replacing a AC split system like for like to the same size heat pump system. After that, however, and this is consistent really throughout the country, if you continue to upsize the heat pump so that you can heat the building to lower and lower temperatures with electricity before falling into that fossil fuel backup, there's really not much benefit. And we even see that in some places, it actually hurts you on the emissions. And you can see that a little bit in Baltimore, that for these gas heated homes, it actually steps up a little bit at the end, because we use contemporary assumptions about the background emissions of the grid. And until the grid is actually close to 100% renewable, there's still emissions associated with using that energy. So that's really just kind of a hint at what things might look like from an emissions perspective. One caveat I'll put on this is that we just use the same grid assumptions for every city. We didn't actually say, well, San Francisco has more solar and hydro, so it's going to have a different heat pump story than, say, Boise. We're really just trying to look at the weather here. So when you see San Francisco, more think of a generic climate IECC 3C, and if you don't know what that feels like, it feels like San Francisco. So then the second part of this is at what price would your electricity have to be to break even on this kind of investment? I'm not going to walk you through every term, but this is just a balanced equation where we set the annual cost of a furnace AC system equal to the annual cost of a furnace heat pump system, and then solve for your price of electricity. And what we found is for natural gas on the left-hand side, in all of these colder regions, regions 3C, 4A, 4B, up to region 8, where heat pumps are really, really uncommon still, to make this dual fuel system work, you really only need your electricity to be less than, say, 12, 13 cents a kilowatt hour. And this is assuming that you're buying natural gas at $1 a therm. If you're buying natural gas at 75 cents a therm, it's more, you would need your electricity price to be slightly cheaper, so less than, say, about 10 cents a kilowatt hour. These are not unreasonable quantities. With fuel oil at $3 a gallon, that's the center dot, the story is even simpler. There's basically no price for electricity seen in this country, or very, very, very few places where electricity is so expensive that it wouldn't make sense to switch over from fuel oil. And that's, again, including the upfront capital cost of going from an AC system to a heat pump. And I'll just show you a little bit. This is just average residential electricity prices across the country. And you really see only in the Northeast, California and Alaska are you able to find prices consistently over, say, 15 cents a kilowatt hour. Throughout the rest of the country, including some really cold places, electricity is much cheaper than that. So this seems like a workable strategy. So that's the first half of the talk. The second half of the talk is where we really dive into the utility itself and how did we get these prices 10, 12, 13 cents a kilowatt hour, and whether or not that's really a reflection of the utilities costs. So I'll just pause for a moment. If anybody has a question, drop it in the chat and I would love to answer it.
Noah, there is one. I don't know if you can see it in the questions. Oh, okay. It says, you mentioned you use the same grid assumptions for all cases. What were those assumptions? 1
pound a kilowatt hour, which is the marginal emissions in most of the country. It assumes a single cycle gas turbine. I will say I have had a lot of conversations about how to do this math, and there's really no consensus about making these assumptions. Just to kind of lead with an example. So there was a paper, an economics paper that came out a few years ago saying, if you adopt an electric vehicle in, I think, North Dakota, your emissions actually go up. And if you do the math and you look at the average emissions in North Dakota coming from coal-fired plants, that is true. Coal is about 2 pounds a kilowatt hour. You do the math and it's just a little bit worse than if you were burning gasoline in a vehicle. Having said that, if everybody in North Dakota started buying EVs, you wouldn't be building more coal plants. You'd be building combined cycle gas, which is going to be something like 600 grams a kilowatt hour, 600, 700 grams a kilowatt hour. So just because something is marginal now doesn't mean it's marginal in the future. And when we're talking about infrastructure scale changes like this, kind of looking at the existing differences in grid emissions isn't actually always as helpful as thinking as what would be built next. You could be a little bit more optimistic and say, well, if demand really increases, say in the Northeast, because of electric heating, because of electric vehicles, the next thing that's going to be built, and this is already happening, is a huge amount of offshore wind. So in that case, the marginal emissions are actually closer to zero. So there's no super clean way to do this. I chose 1 pound a kilowatt hour because I didn't want to make the case too easy for electrification by just assuming that it was renewables or even combined cycle. We took single cycle. Any other questions I can't see?
Yes, there's 2 more. This person, this attendee would like to know, the economics do not seem feasible in New York. Can you provide your opinion?
Yeah, so right now electricity in New York is too expensive. And actually, I'll get into the second half of the talk. That frustration, because I live in New York, is really what got to me and led to basically the last 18 months of work I've been doing, digging into utility economics. So I'll address that next.
Okay, so we can come back to that at the end of the presentation.
Yeah, if I haven't answered it sufficiently at the end, ask me a more detailed version, and I'll definitely would love to talk about that. Okay. So when you buy electricity from Con Ed, you think you're paying for the power. The truth of the matter is you're mostly paying for other things. Electric utilities are utilities. They're natural monopolies. They are regulated companies that are the only supplier of some sort of commodity in a region, specifically because they operate in industries with very, very high fixed costs. In the early days of electric utilities, there was competition. You'd have multiple electric utilities trying to serve single customers. It was a mess because you were trying to build all these different wires and poles overlapping. So the natural thing that happened was these different companies would merge together, they would form monopolies, and then they would charge monopoly prices, which is a nice way of saying whatever they wanted. Today, we regulate electric utilities so that they can only charge us a reasonable amount instead of as much as they want. But the thing that hasn't changed is that their fixed costs are really high. And when you add up the actual generation assets, the transmission lines, the distribution lines, their administrative costs, all these fixed costs that don't actually vary with my marginal consumption of another unit of electricity, it's huge. So this is data from the Federal Energy Regulatory Commission filings. All the utilities have to submit their financial data every year. We're specifically, just in this plot, looking at utilities with regulated generation because it's easier to keep track of their power production costs than a utility like Con Ed, which buys its energy from the market. So power production is far and away the biggest cost for utilities, the actual cost of fuel, cost of coal, what have you. However, if you add up all of their administrative costs, their distribution O&M, their distribution CapEx, production CapEx, so that's the cost of the turbine, but not of the gas, and all of their transmission expenses, it basically rivals power production costs. And in places like New York, Con Ed, it's actually significantly more. So how is that handled? It's handled differently for different customers. For commercial customers, you typically pay a demand charge. So your allocation, the fraction that you pay of a utilities cost, is proportional to your peak consumption over a 15-minute period or over an hour period in a given month. Residential customers overwhelmingly pay through a volumetric charge. So I take, some weighted average of the cost of power. I add a couple cents a kilowatt hour to cover all of those fixed costs, and that's how you compute your 10, 11, 12 cents a kilowatt hour. This is a problem that's been pretty well studied in the economics community, and it's kind of a hot topic right now among energy economists. So let's say, I'm going to walk you through this hypothetical, and this is not my work, this is from an economist at Berkeley, Severin Borenstein. So let's say the marginal cost, if you imagine a utility that only has single cycle gas turbines, and when you shake it out, it costs them 5 cents a kilowatt hour to produce every single kilowatt hour that they sell me. Now, if I only paid that 5 cents a kilowatt hour, they wouldn't have the money to provide the distribution infrastructure, the generation infrastructure, the transmission. So what do? They charge me more. So instead of charging me 5 cents a kilowatt hour, maybe they charge me 11 cents a kilowatt hour. Now this slope here is called my demand curve. My demand curve is pretty inelastic because I'm a traditional passive customer. If I want to plug in my computer or use my microwave, I am going to do those things. If my electricity costs more, I might be frustrated about it, but my consumption is not going to change very much over, say, a month. So what happens when you raise the prices, there is a deadweight loss because there's some quantity of power that I would have consumed at 5 cents a kilowatt hour that I'm not willing to consume at 11, but it's small. It's the small little wedge, and that is electricity that they could have provided to me that I might have been willing to pay 6, 7, 8 cents for, but I'm not willing to pay 11 cents for. And it's a real inefficiency, a real loss in the economy. So that's your traditional passive customer. Now, if you think about today's customers, when we're talking about electric vehicles, you may or may not purchase an electric vehicle depending on what the incentives are. You may or may not install the heat pump. And just as we looked at in New York, heat pumps don't really shake out. There's a much more elastic curve. So it's a much steeper slope there, or it's a shallower slope. So when you've got somebody who's making these bigger decisions, that change in the price of electricity creates a much bigger deadweight loss. And what's contained in this triangle is the heat pump that somebody doesn't install, because even though the cost of electricity to power it was only 5 cents, or say was only 5 cents, the fact that Con Ed was asking for 21 cents to sell me that electricity means that I wasn't going to do it, and I'm just going to keep burning gas. So the interesting thing is, if we just want to get down to real numbers, if you take a 2,000 square foot home, that comes out to about 100 million BTUs, based on some assumptions we're working on, say 100 million BTUs per year for heating. If you take the electricity, sorry, this is specifically looking at National Grid upstate, based on their average electricity price, including the delivery tariff, if you wanted to do all of this with a heat pump, it'd be about $1,000 a year. Now, on the other hand, if you're buying natural gas, still from National Grid, and you're paying their delivery charge, it's between $500 and $700 per year. However, if you actually look at the commodity prices, so not looking at the fixed costs for the transmission, the fixed costs for the pipelines, but just looking at the cost of gas and the cost of electric energy and losses, they're actually really close. The cost of providing that energy, again, this is for 100% electric heating, not the dual fuel thing we were talking about, but 100% electric heating with a backup of electric resistance for very, very cold temperatures. You'd actually even see slightly cheaper, it might be slightly cheaper to run the heat pump than the natural gas. And it's just this kind of vestige of how utilities have structured their rates that makes it appear uneconomical, even if it really isn't. And I should say that utilities are super slow to change. The reason that we have volumetric charges and demand charges today in 2020 is because 100 years ago, there were really only 2 kinds of meters. There were meters that could measure volume, and there were meters that could measure peak. And it's only more recently that you could even gather the data that you would need to charge people based on the intricacies of their actual energy profile. Now, utilities aren't totally naive to this, so there are tariffs out there specifically for electric heating in homes. This is based on a little kind of mini project I did with an undergraduate researcher last year, where we took data from the US Utility Rate Database, which is managed by the EIA, and we found that there were about 600 utilities that have some residential rates specific for electric heating. We then went to those utility websites, we actually dug into those rates, and we realized that there was really not like common sense to how they structured them. So for example, Connecticut Light and Power gives you a discount on your volumetric rate, but then a much higher fixed charge. And that's shown on the bar graphs at the bottom. Per kilowatt hour, if you are on their electric heating rate, you're paying about 9 cents instead of say 11.5 cents. However, there's this huge upcharge on your monthly fixed charge on the bill. So instead of paying about $9 a month, you're paying like 24. And we did the math, and this was a lot of fun, and we found that if you have a really big house, you do save a lot of money. So if you've got a 5,000 square foot mansion in Connecticut, then this is a great offer for you, and you should be heating with heat pumps. But if you've got a smaller home, say 1,200 square feet, you actually are going to lose out in the long run. Different utilities have different piloted rates. There's time of use rates. Con Ed recently introduced demand charges for residential ground source heat pumps. a couple of utilities are using increasing or decreasing tiered rates. And you can run through the numbers. There's very little logic to, are these even incentivizing customers to adopt electric heating, let alone are these actually reflective of the utility's real costs. I think one of the reasons that utilities are a little bit concerned about wide heat pump adoption is that air source heat pumps in particular, and all heat pumps to an extent, are really, really peaky. And you get that from the weather. In New York, for example, you know, in the summer it's in the 80s. It can get up to the 90s. It very rarely gets much hotter than that. In the winter, that risk is much different. So a lot of the winter, it's in the 30s, maybe even 40s. Sometimes it gets into the teens, but then you have these amazing cold sprees where it gets into the negative numbers, and it's really hard to be prepared for that. So what we did here is we modeled different levels of heat pump adoption on an example feeder located in upstate New York. The gray line that you can see underneath here is the existing feeder curve, where this black is the average daily consumption, and the gray is represents the maximum and minimum consumption. If you add electric heat pumps to 20% of the homes, backed up by resistance, you find that, as expected, it doesn't actually change the demand at all in summer, but in the winter, it does change the demand. And even at just a 20% adoption, this one really cold day that they had in January of 2019, I think, is enough to actually push the load all the way up to the feeder's capacity, not the red line. If we went up to 50% heat pump adoption, we would need to add almost twice as much feeder capacity just to plan for that one really, really cold night that may or may not happen once a year. And if we go to 100% heat pumps, the case gets even uglier, which is really kind of, you know, if I don't have you convinced on dual fuel already, I hope this convinces you that it's something to consider, not just for the building owner, but for the utility. This is a really hard thing to plan for. This is a really, really expensive utility system. But again, if you're backing it up with some sort of liquid fuel or gas, something you can combust for those few really bad days, then you could actually end up with a better use of existing utility resources. So this is basically where I'll leave you. We've been doing just a little bit more work on this, trying to figure out optimality. Basically, the project is we know what it actually costs to procure electricity. We have an understanding of what the utility's fixed costs are, how much it might cost them to expand a feeder's capacity, and we're trying to figure out what is actually the optimal way to do heat pumps, to do electric vehicles, considering all these technical constraints. And then based on knowing that function, we would then say, what are the least bad tariff structures? Now, we know volumetric tariffs can be really ugly because customers have to pay that same additional 5, 6, 7, 8, 9 cents a kilowatt hour, even if their consumption is happening off peak. But what's an alternative that might be something that customers would be admissible of, and also would allow for some decarbonization? So in conclusion, hybrid systems, really promising, big emissions reductions potential, and that is going to keep going up as the grid gets cleaner. And then the other thing to think about is that if you're hearing talk about redesigning electricity tariffs into something more complicated, know that it isn't just to punish you, that there may actually be some societal level benefits to giving slightly more accurate price signaling. Here's some bibliography and some of the references, and I will take any remaining questions.
Thank you, Noah. There is a couple of questions that come in. There's one from the first part that we did not answer. I just want to make sure we get an answer for our attendee. It says, you said your break-even calculations included the upfront capital cost of a heat pump system. Is that assumption the total cost of the new heat pump system, or the difference in cost between the heat pump and replacing in kind?
Difference. Very good question. I'm sorry if I wasn't more clear about that, because it is really important. The idea is, what should we plan for when air conditioners die, which they do. Most homeowners, if their air conditioner gives out in July, they're going to try to get an exact same new one as quickly as possible. We're trying to understand if maybe the heuristic, if the rule of thumb instead should be, I'm going to replace it with an in-kind heat pump, which is only a little bit more expensive, should be the same install cost.
Next question is, in areas like New York where electric rates increase, heat pump operational costs during the heating season. Sorry, I'm going to restart this one. In areas like New York where electric rates increase heat pump operational costs during the heating season, did you investigate if energy savings during the cooling season will offset?
Oh, that's a good question. So yeah, I mean, if you, at least in that first paper, we were only looking at an air conditioner with the same, you know, an AC versus a heat pump with essentially the same operational properties. So yeah, you're not really thinking about replacing, I guess I haven't done the work of looking at replacing like a 14 SEER AC with an 18 SEER heat pump. It's a good question. I don't have an answer to that.
Next question is, does this include any amount of energy storage, i.e. the top of many or most of the points are nighttime, but even a resistance heater in a brick may change the cost of the curve in a good way?
Even a resistance. Yeah. So no, I did. First of all, I didn't include storage in this. Storage works really well if you use it consistently daily in kind of the same way. So the prices we're seeing right now for distributed storage are on the order of, say, $500 a kilowatt hour. I think there's ambitions for, this is for lithium ion batteries, to get it down to maybe $200 a kilowatt hour. And if you shake it out, you know, if you're using it every day, say coupled with photovoltaic panels, it can pay off. If you're trying to use it just a few days a year and you don't have any other use case for it, it's not going to work as well. So you would probably want a different system for planning for those few days in the winter. And it's a good point, even electric resistance heating, if you're storing the energy, could be fine. What I imagine is either we would need some, you know, there's lots of novel storage strategies other than just what we think of when we think of storage, which is mostly batteries. So there are all kinds of like pilot projects trying to bring on in big seasonal storage into the grid, which would be higher variable cost and lower fixed cost, like a peaker plant, kind of like peaker storage. I think having, you know, I think ironically, one of the things that came out of this project is that even like a fuel oil tank, and we've been moving away from fuel oil in the Northeast as quickly as we can because it's expensive and it's really emissions intensive, but it's also stable. So even a fuel oil tank in your basement, if you're only going to use it with a furnace for 100 hours a year, and having that enables you to go to mostly using a heat pump, could actually help you save emissions in the long run. So that was a lot of words. To make it short, there's so much room for so many different interesting technologies in this space. The barrier for a lot of them, though, to actually having this experimentation come to market is that the rates are really archaic. And we really need to get smarter about creating incentives for entrepreneurs to come in and try this stuff. And at least in the residential space, there isn't enough of an incentive right now.
Actually, that leads into our next question, because it says, have you encountered any similar studies in commercial sectors?
Similar what?
It says similar studies in commercial sectors.
Yeah, there's some stuff in this space. So trying to think. You know, with commercial, all the kind of optimization studies where you're looking at DER adoption in the commercial sector, it's always about managing a demand charge. So you end up with all of the optimization trying to make the demand from the building as flat as possible, because you're trying to avoid having any kind of peak consumption, any kind of peak standing out for the individual building. Yeah, I mean, there's a decent amount of work here. If you reach out to me, I can probably point you to some interesting articles.
Next question is, do you have any data on an actual utility fuel mix to figure out the actual emissions from generation and check if your conclusions about heat pumps still hold true?
Yeah, so I have all that data. I mess around with it. I chose not to use it in the version of the study that I shared at ASHRAE. If you're interested in seeing the actual historical emissions from the grid, Google EPA eGrid, and the most recent data I think is from 2016, and it will show you both the average emissions in lots of different little sectors throughout the United States, different kind of nodes of the transmission system. And that ranges from, you know, the least you'll see is say like 700 pounds, sorry, 0.7 pounds per kilowatt hour up to like 2 pounds a kilowatt hour. And of course, yeah, if you plug in very different numbers, you'll get different results. But I am pretty steadfast on this point that I made before, that when we're thinking about electrifying heating in buildings, which is north of 10% of all of the energy we use in this country, we can't only be looking backward at what generation already exists. We need to also be thinking about what are we actually going to build to meet that demand, and it's not going to be coal. Unfortunately, it's not going to be nuclear or hydro either. So it's you know, we're basically stuck with renewables and gas at this point, which all have, you know, benefits and have vices.
Okay. Next question. Have you studied the impact of combined solar PV and ground source heat pumps?
Have I studied the economics of PV and ground source?
Yeah, they said, have you studied the impact of combined solar PV and ground source heat pumps?
I have not. It's hard to get a number on ground source. Probably we all know Bob Wyman. Bob Wyman's affiliated with a company called Dandelion, and he seems to be everywhere. And he and I have had a couple of interesting conversations about ground source. What he always tells me is that the most expensive thing about ground source is getting the equipment to site. And then once you've drilled one ground source hole, you can drill 100. So knowing that, I think ground source probably makes a lot of sense if you can do it at scale. But I've also heard numbers that if you want to do a ground source well one-off, it's something like $30,000, which is never going to break even on a retrofit project based on the current prices of fossil fuels and electricity. So the margin's simply not that big. PV, I have strong opinions about PV too. I think we need huge amounts of PV on the grid. I didn't get into this too much, but one of the reasons the economics of rooftop PV as photovoltaic solar panels the economics are as good as they are, is actually again because of volumetric pricing. So in a place like New York, if I produce a kilowatt hour of energy from my rooftop solar, that's a kilowatt hour less that I'm buying from the grid. So I'm saving 20 cents more or less as a volumetric customer for every kilowatt hour that I produce behind the meter. Now the actual value of that avoided energy could be 2 cents a kilowatt hour. You know, that's the actual price going through NYSO these days. So it's, I would say that that's kind of the other side of this. And I think my last slide, this optimization actually allowed for solar. It allowed for picking solar to offset demand anywhere it wanted, and the optimization does not pick solar. And in more recent iterations that I've been working on, the price, the actual cost of generating electricity would have to rise above 20 cents a kilowatt hour. And again, it very rarely rises above, say, like 4 or 5 cents a kilowatt hour, but it'd have to rise above 20 cents a kilowatt hour for it to be economical to adopt any solar to offset either your peak power consumption or just to offset your total volumetric energy consumption. So just in brief, we do need lots of solar. I don't know that it should be on people's roofs.
Next question. Did you model cold climate air source heat pumps? At what temperature do you assume the heat